So hi everyone, I see that people are just joining in. I will start by saying thank you all for joining us. Thank you Trevor for joining us also and giving this lecture to the Israeli community. As I mentioned in our post, this is a series of lectures from top professors and researchers worldwide. And we are honored to have Trevor here with us today. And basically, how it's worked, Trevor will give a lecture today, and later on we will have a Q&A sessions. Before that, Bruno from Nexar, the co-founder, will give some slides about Nexar and what they are doing, and then we could start. Um, that's it. We will send later on a link so you could ask your questions and then to upvote the relevant questions for you. And then in the Q&A session, we will ask those questions. And that's it, Bruno. Do you wish to start?
Yep, sure. Thank you, Uri, and thank you really for joining. Hopefully, we go the next 60 minutes will be a good use of time, and we look forward to listen. So I just wanted to spend a few minutes to brief you a little bit about Nexar. You make things that add value. So we work. The reason that we managed to sell these 100,000 cameras is that we have an ecosystem of people that work with us, like Scotch or ASCII, which is a subsidiary of Asus. They make their own cameras, they sell their own cameras, but they're compatible with Nexar. And anytime you drive with them, those are also helping really understand the real world. There is a bit of deep learning models running on the cameras. There's a bit of deep learning models running on the cloud. The main reason that people do this is because we close the loop with the dash cam. So if you have a regular dash cam, it has a little SD card inside, but it's not that very useful. So we connect it to an insurer. So when you really have trouble, you get the insurer to help you. And finally, this comes down to now really after we get all this data, applying AI to analyze it, right? And there are two sets of products that we're doing with AI that help us. The first one is make sense of these images. So if you look at these, on the previous slide, these trillions of images that we have, if we were to even pay $1 on GPU cost to analyze them all, we'll be spending like $20 million to just make sense of them. So you need to create the index smartly. You need to apply AI smartly. And then once you have the images and you understand the images, you need to start putting things into the real world in terms of objects and how they move. And that's where the maps, fresh maps of the road come into place. But the first one with the images is definitely privacy and making sure that, what we are uploading, it's only used to help our drivers and to create data products out of that. So, we do things like face blurring, license plate blurring, classic things. All the things that we're doing within networks is, for example, pixel level segmentation to identify any other privacy markers around the windshield or the dashboard that should be removed and masking them, as you see on the right. Even to the extreme, as you see on the bottom left, there is a phone projection on the windshield, hallucinating what actually should be there to remove that marker from the windshield. The second thing is that, again, 2 trillion images is a lot of images, and not all the images are equal. So some of them, like the top left, has higher value, so it has higher ranking in the image index. And the one on the bottom right has much lower ranking because it's mostly elements that get masked by the previous algorithm that was showing. Then comes things that we're doing, very, very recent around superglue, being able to specify a query patch, which could be out of any image, could be out of, for example, Google Street View, and then going through the database and matching all the images that you see with the little patch in green that will contain that as part of in our data set, to making it really useful. And then the final step on the images, obviously, is that you need to put the images somewhere, and this is part of the work that we've done with Trevor and got accepted and presented last year at CVPR, and it's the link there. But essentially, it's a coarse to fine-grained approach to to really look at markers and start going down to self-supervised network to help us end up, you know, in that progressive mode to really localize ourselves. Then once, you know, you move to the second part, which is, okay, these images are great, but you need to put them somewhere. You need to understand the world. That's where objects come in. Those are traffic lights, road signs, lane markings, cones on the road. You have, you know, we do things like detection, video-based 3D reconstruction and depth estimation, parking space detection, super useful feature for finding parking spots, you know, unlike other apps that, you know, you only see what other people have left, or things like lane closure recognition. So, you know, actually the roadworks are in this road and I know that is the right lane that is closed. And finally, you know, change detection, right? So we do a scene, we understand the scene change, and within the scene change, we're able to understand the object change. So you see on the left, how the left has been changed to the right over time. You know, the median and the palm trees are gone, for example, there's a bit of roadworks, or there is construction missing on the left and there is construction roadwork gone on the right. So both the addition and the removal on the scene become objects that are added or removed to the base layer, to the map. And all this information, as I said in the beginning, gets back to the beginning. None of these would have been possible if we tried to do everything on the cloud or everything on the device. And I think part of the unique thing that the team has been working on is to have this flexible hybrid compute that sometimes part of the network runs on the mobile phone, sometimes the network runs in the cloud, sometimes it runs on both. So, you know, you extract the embeddings, send the embeddings, and then continue. So it's all sort of combinations that we're running. And, you know, I think the last one that we started to work on a couple of quarters ago is to go beyond the device and beyond the cloud, looking into 5G about how can we run on the edge data centers, the multi-access edge centers, MEC, that are coming with 5G. Like CDN was for YouTube. I think this is going to be a big trend. And, you know, you all seen the news with NVIDIA and ARM around this, so I don't need to tell you more about that. So all of these wouldn't be possible, obviously, without a great research team. And, you know, and I think a research team wouldn't be great if we didn't have Trevor with us. Trevor is our chief scientist at Nexar. He's also a professor at UC Berkeley. He's co-founder of Bear, and he's been working for over a couple of decades on computer vision, and he's very, very excited to do that. And, you know, so I would like to welcome Trevor. You know, I'll put my hands together, but we're all muted, and look forward to a lecture. Thank you. Thank you, Trevor.
Great. Thank you so much for that very generous introduction. And I wish I could be in Israel right now presenting this live. Really enjoy all my trips there and engaging with the team, hoping for 2021 to be when we can do that again. I've just started screen sharing. I hope it's visible. And I also, and so now I am in presentation mode. I hope you can everyone see this? Someone give me a.
Yeah,
yeah,
we can
it's
see
good.
Well.
Okay, great. And you know, the other, I enjoy giving these talks over Zoom. It makes it really easy for lots of people to attend, which is a great advantage. But it means I don't get any feedback in real time from anyone. So feel free to ask a question verbally, or you know, if something is super confusing, I'd be happy to get feedback in real time. Today I'm going to tell you about our recent work in fully unsupervised learning. Also, if time permits, advisable and explainable AI. I might push that a little bit to the Q&A session, depending on how things go. And I think this is relevant to Nexar and relevant to many companies out there in the world and academic projects. The promise of supervised learning is, of course, has been realized to a great degree. But we all know how futile it is to try and label every possible configuration of the world, everything we're interested in. And so the real excitement right now in the field centers around how we can move beyond supervised learning to forms of learning that are unsupervised, self-supervised, or adaptive. And this is very popular right now. Several memes are out there expressing this as the revolution, a foundational aspect of deep learning. Jan LeCun has this great metaphor of the cake that he's used, and unsupervised, self-supervised learning is the cake part. It's not the icing or the cherry. I'm not really sure this is the right metaphor. It's not really a balanced food pyramid. I think unsupervised learning is probably, you know, the grains or the healthy part of the meal. But we all get the point. And in fact, this is a very almost a dominant paradigm in research right now, showing that different forms of self-supervision can replace or nearly replace the need for manual labels in many settings. And self-supervision is an old idea that's become new again, and it's a quite cool and exciting one. And it's in contrast perhaps to real classic unsupervised learning, which would be more algorithms for clustering or dimensionality reduction. Here, self-supervised learning constructs proxy tasks, such as to predict one half of the signal from another half of the signal, or to predict one modality like color from another modality like appearance, to predict geometric relationships such as in the jigsaw puzzle, context prediction, take an image, slice it up into pieces and see if you can put it back together, or simply rotation prediction, rotate an image and see if you can predict how much it's been rotated. And these tasks have turned out to actually be not as good as supervision, like in a targeted task, but almost as good and therefore much better, because you're never going to have supervision in all settings, in all domains. And so these tasks can give you a strong signal with which to do representation learning. So that's good. But let's be a bit careful here, and there is some reason for concern. The worry I have that I'll outline in the following slides is much of the contemporary self-supervised learning research actually presumes knowledge of the target domain of a downstream task. And we've moved away from feature engineering to deep learning, and I want to make sure that we're not just replacing one form of knowledge with another form of knowledge, or in fact, that's what we're often doing in the contemporary methods. We're actually doing augmentation engineering. There's human knowledge of what invariances are present in the downstream task. Actually, that's very cool. And I think that's the right way to express some of the existing work, that instead of having to put labels in the target domain, a human expert can tell you what invariances there are in that domain, and you will do data augmentation to make your representation better. But what we're pushing on now, and what I'm going to report in the rest of this first part of this talk, are methods that are actually fully unsupervised, which don't require this kind of prior knowledge. So here's an illustration of the problem. This is a figure from one of the famous papers in contrastive learning. And in that paper, it's very clear they tuned the transformations to find those that are going to work on ImageNet prediction, which is great because that's what their task is, and that's in fact the task that everyone pays attention to because it's a famous leaderboard. But in the real world, we're going to have some other kind of condition, and the real world is not going to be ImageNet. The real world may look very strange. And we can't presume that we're going to be able to actually have labels and do that kind of augmentation exploration. So it's somewhat of a cheeky tagline to this talk is what do we do when your unlabeled data doesn't have any labels? And you don't have any knowledge about that domain that you're going to impart into your method by providing invariances. So there's 3 microtalks in here that I'm about to go through. Each of these is a paper that's on arXiv. So if you're interested, you can find out the details there. The first is what should not be contrastive in contrastive learning. We've built a method that actually is much less sensitive to hand selecting augmentations. And I'll go through that, sort of a multitask approach to self-supervision that bakes in selectively removes through a kind of a leave one out method invariances in each of several heads. The second is a very simple but powerful idea, quite independent and complementary to the first, that rotation prediction is actually a meta self-supervision task, or at least empirically we observe that to be true. And in fact, rotation prediction as a task can predict what augmentations you should use in a self-supervised paradigm, a contrastive learning paradigm. And then last, for the unsupervised part of the talk, I'm going to pivot slightly to adaptation, domain adaptation, which is an area that we've been working on for many years in my group, and show a very, very simple, sort of lightweight, can be run easily at the edge on an edge device, domain adaptation method that simply works by maximizing model confidence, entropy-based normalization technique at test time. And we call it fully test time because that method certainly doesn't have any downstream labels, doesn't have any target labels, and it doesn't have any hidden knowledge that a human imparts in the method after they look at the target domain. And that fully unsupervised adaptation method doesn't even have access to the source data or source distribution. Many methods for domain adaptation that we've worked on are based on alignment. And so this one doesn't even use alignment, it just uses the weights of the model and the unlabeled test data. So that's what we mean by fully unsupervised or fully adaptive. Very excited about all these ideas. And so hopefully I can get through them in enough time, and then I'll give a snapshot also of our advisable and explainable work at Berkeley, but I think that'll just be a bit of a teaser. So what should not be contrastive in contrastive learning? I've already told you the problem of the methods, current self-supervised methods that are yet very successful, but do presume a hand-provided set of augmentations with which the method learns. In contrastive learning, we take a query image, we typically transform it with some number of transformations, here a rotation and a color transform. And then we learn a model that, we learn embedding in which those 2 images are projected to points that are close together and far from negative examples, which are other categories or other images, other instances. And this is great if you know ahead of time the invariances of your target domain or your downstream task. But the existing methods can underperform, as we saw in that empirical chart of different augmentations. If you pick the wrong augmentations and your task is actually sensitive to rotation, and you transform all of your data with rotation augmentations, you're definitely losing something. So here's an illustration of that. Here are different classes and different kinds of augmentations, color, rotation, and texture. And for ImageNet classification performance, actually some of them are useful and some of them not so much. Color augmentations turn out to be useful for ImageNet classification. Texture, definitely, some texture transformations. But actually rotating your training data, adding that augmentation to the training data doesn't help in ImageNet. It turns out that upside down elephants aren't very common in ImageNet. And so best to let the data speak for itself in terms of rotation statistics. But if you look at another task, like fine-grained recognition, well, actually, color and transformations aren't actually a good idea there in that setting, because color is very discriminative for certain fine-grained bird species. So you wouldn't want to add color augmentation if you're doing fine-grained classification. But for some fine-grained classification, rotation invariances are good. For flower classification, for example, if that turns out to be your downstream task, then you would have liked your augmentation strategy to include rotation, but not color and texture. So, so right now, the state of affairs with contemporary self-supervised learning is that the human practitioner has to know ahead of time what the target domain is so that they can specify what augmentations to use, or they actually have to have labels in the target data with which to do this cross-validation of which augmentations to use. And that's sort of presuming that you have labels in your unlabeled data. Okay, so, so jumping right to the chase of our new method, I'm going to kind of present it all in one shot. And if you want more details, indeed, there's an archive. We've taken the ideas of SimClear and MoCo and expanded them to have what we call a leave one out paradigm. So we have a multi-headed leave one out paradigm. We indeed take images such as image Q on the left. We have a set of transformations, in this illustration, rotation and color. And what we do is for each of several losses, for each of several heads, we're going to do all but one of those transformations. And there'll be one that has all of the transformations as well. So the base image Q is transformed with both color and rotation to get K0, with just color to get K1, and with just rotation to get K2. So the idea here is we want a representation which doesn't lose sensitivity to the augmentations. In the traditional model, where we have a single compounded loss, we'll learn a representation that's going to sort of be less sensitive to the augmentations that we include in our scheme. So it'll be less sensitive to rotation. If it turns out your task is sensitive to rotation, like flowers, you're somewhat out of luck with the learned representation. Here, because we have multiple heads, one of our heads will be sensitive to rotation. Another one will be sensitive to color. And so in the end, if our downstream task needs sensitivity to one of our augmentations, it will find it. And now there's two different strategies we've explored with this approach. So each of these spaces, Z1, Z0 to Z2, has the loss corresponding to all but one of the augmentations. And there's a layer beneath them, the general embedding space V, which is the bottleneck through which learning proceeds. So one approach is just to take that bottleneck layer, V, and use that as our unsupervised representation. Another approach is to concatenate the leave one out variant dependent embedding spaces. And so we will show results with both. We find that the second one is slightly more effective than the first one, but they're both strong advances over the previous methods in this regard. And we're showing it for 2 in this illustration, but it can be extended to more augmentations. So the first thing that we sort of illustrate is that using our multi-headed leave one out contrastive learning method, a downstream task will end up using the part of the representation that's most effective. So for example, when you do end up checking performance on ImageNet, with an ImageNet classification as the classic downstream task, it turns out that texture is the most significant head or channel that ends up being useful for the representation. In contrast, when you look at a fine-grained task like iNaturalist, it tends to use all of the representations, which is consistent with the intuition that we showed in the motivation slides. And the quantitative evidence comparing performance on a range of different tasks, including ImageNet, but also these fine-grained tasks, bears this out. So the good news, starting all the way on the right-hand side of the chart, that's ImageNet performance. This is sort of a standard benchmark of how unsupervised or self-supervised learning is doing. The good news is Luke doesn't do any harm. MoCo has been tuned for ImageNet. The transformations that work on ImageNet have been the ones that are added into MoCo. So it gets great performance. And with Luke, we can add rotation and variance into the model. If you add rotation and variance into MoCo, performance on ImageNet drops considerably. we can add rotation invariance into, and that you can see that chart in the paper. I didn't put it in the slides here. We do no harm on ImageNet, but on the fine-grained tasks, MoCo misses out because it doesn't have all of the possible augmentations that are useful, and in fact, it has color may actually harm. And our method includes them all and lets whichever ones work come to the task and lead to improved performance. So we show improved performance on iNaturalist, on Cub, and on Flowers, and match the baseline performance on the coarse grain task, ImageNet. That was an experiment where we were pre-training on the small version of ImageNet, ImageNet 100. Also, the same happens on ImageNet 1K, tested on 1K. So even as we have enough GPUs to run these larger experiments, we get the same trend. So that's the first part of the story here. If anyone wants to shout out a question, I'm happy to take it. I'm just going to plow forward and try and get through the rest of these slides so I can touch on next thing at the end. So there we've learned we've proposed a new multi-task version of contrastive learning with a leave one out strategy, so that we learn representations that sometimes have the benefit of the augmentation, but also have parts of the representation that are sensitive to that transformation in case the downstream task cares about it. This is now a complementary work here in collaboration with Kurt Koitzer's group, where we make a similar observation to address the same problem, which is perhaps we can find a cue which is correlated with actually having labels in our on our downstream task. And if we can, that would be quite useful. So in fact, we ran an experimental investigation of a variety of different kinds of tasks to see if there was one cue that turned out to be more useful than the rest to predict what augmentations would end up being useful for target domain. And the observation of this work is that rotation prediction actually, for a wide range of domains and data sets, turns out to be almost as good a task as having labels in your downstream setting, at least for the problem of doing this cross-validation of what augmentations to use. So the way this is visualized is through scatter plots. Here, each point in one of these scatter plots is a different run of self-supervised learning with a different set of transformations or a different set of augmentations baked into the run. So for example, the gray dot might be having translation in X, the blue dot might be having translation in Y, and the orange dot might be contrast. And we want to see, is there some self-supervised task that actually is going to be predictive of performance on the downstream task? That would be linear. The y-axis is performance on the downstream task. And the center plot shows that the accuracy of contrastive loss itself isn't really that correlated with performance on the downstream task, nor is a measure such as info NCE. But linear rotation accuracy, prediction on the rotation task, does seem to have a linear relationship with performance on the downstream task. And this turns out to be true across a wide range of different data sets, including all the ones shown on this chart. We see that the y-axis is downstream task performance, and the x-axis is rotation accuracy prediction. And these are some pretty linear relationships. And so this turns out to be useful in practice, not only for selecting what augmentations to use, but also for specifying parameters of those augmentations. Linear rotation accuracy is most effective at predicting the parameters of these models as well. So this turns out to be useful in a similar way as the previous method. It can find the right augmentations to use to achieve performance across a range of these tasks that is competitive and sometimes exceeds the MoCo augmentations. So we call this self-augmentation, using rotation prediction to decide which augmentation strategies to use. This is not only relevant for choosing augmentations, but also potentially for choosing architectures or architecture hyperparameters. And the archive just went up on this in the last day or two, or in the next day or two, if you want to see more about that. So the last part of this talk is pivoting to adaptation. Whether we've learned a model with supervision or self-supervision or semi-supervised model, we will be deploying it in the real world, and the real world might change on us, as it did for us in UC Berkeley last week. I can report from the Bay Area that it rained this morning, and our air quality turned very good yesterday. So it's a relatively nice day in the Bay Area today, if rain is a good day, which it is. But you must have seen the media reports of our orange sky last week. It turned out that orange sky day wasn't the bad day. The orange sky day just felt like the world was ending, but the air quality at ground level was actually pretty good on the orange day. It was the following 3 or 4 days, which were just regular gray days, that the air quality turned to be world-class bad. But we got through it. But our computer vision algorithms didn't necessarily fare so well. If we take models that are trained for semantic segmentation and run them on these orange sky images, I hope everyone on the call is familiar with semantic segmentation and cityscapes imagery. I'll show what it should look in a few slides. But here we're running a standard fully convolutional model that's trying to predict scene labels, where each color in the image on the right corresponds to a scene category. And you can tell this is not a good answer. And this overall change in the environment, which was not present in the test set of this model, makes the model perform catastrophically poorly. And of course, the model doesn't even know that it's performing poorly. Now, in the method I'm about to show you, our domain adaptation method, with no labels at test time, it can fix the model so that it's not so surprised by this input, and performance can be better. Here's another orange world example, and our adaptation model brings it back. You can finally see the person, but it's not perfect. The other person's still missing, and so on and so forth. So many of you may already be familiar with the paradigm of domain adaptation. We've been working on it in my group certainly for many years. And actually I'll step back and give a little overview of different approaches to adaptation. Actually fine-tuning a model, especially a deep model, is a very reasonable approach to domain adaptation. Of course, that requires you have labels in the target domain upon which to fine-tune. Deep learning itself is actually very useful for domain adaptation. In fact, domain adaptation is how I got into deep learning early in the 2010s. Deep representations are inherently less sensitive to domain adaptation than the models that we had used previously, before deep learning kind of retook everyone's attention. But even deep learning models, as we just saw, can still suffer significantly from domain shift. So I'd say the main body of work that's happened in the field, in my group and in others, on unsupervised domain adaptation, meaning we don't have any labels on the target domain, is based on an alignment paradigm, where we say, I'm not sure what's going on, I don't have any labels in the target domain, but I should learn a representation which looks similar on the target data and on the source data. So we do some joint training or alignment between the two domains. There's also a paradigm of self-supervision, where we use a self-supervised task to use that as proxy labels on the source domain. But that requires knowledge ahead of time of what tasks are useful. So actually, I'll go through this in a few more details on these slides. Repeating a little bit what I just said, fine-tuning is great, but it's extremely costly or infeasible to assume that you're going to have labels in every possible condition that your model will experience. Unsupervised domain annotation is great, but it's actually a pretty complicated method, and it requires that you still carry along either the source data itself or a representation of the source data, such that you can do an alignment method when you encounter new test data. One of the most successful models that we've explored, and others as well, have been based on adversarial losses, essentially a GAN-style architecture that's applied to domain annotation, was sort of developed around the same times as GANs independently by several groups. And here we basically say, I'd like to learn a representation upon which a classifier cannot predict the domain label. And we use an adversarial loss from that domain classifier to update a source model to learn a representation where the two things are confused. So this is still a good idea. Feel free to look at our work on domain confusion and FCNs in the wild, and the method from Gannon and others for this type of model. But it assumes that you have the source data around. In this work, we're targeting what could you do really on a very lightweight edge device, where you're not going to want to run an adversarial GAN training scheme on your Raspberry Pi or whatever your Jetson is at the edge of your, or the tiny sliver of your iPhone that you have allocated to your app out at the edge. So we're calling this fully test time adaptation. It's label free, source free, and proxy free. We don't ahead of time know which tasks are useful or not. This is useful for that setting that I just already outlined to you. So jumping right into the method here, what is it? On the left here, we show illustration of just standard supervised learning. On the right, we show this idea that we're going to normalize our representation using an optimization only on the target data. And the optimization is going to be an entropy minimization. And this actually is inspired by very classic techniques in computer vision, pre-deep learning. Anyone with enough gray hair, maybe there are a few on the call who remember SIFT transformations and scale space. Maybe you at least had to take a computer vision course that expressed those ideas to you. And there the idea was you would find invariant features that were extrema of some optimization or some entropy property. And that those would be kind of landmarks upon which a representation would be more stable. And that's the same idea we're bringing here now to sort of deep learning approach. And it's very similar to ideas that have been used for batch norm and batch norm for domain adaptation, but we take it a few steps further and build a full affine transformation on the data and show that performing that normalization at test time and at training time leads to really improved performance and robustness to domain adaptation. So I'm going to just show the results, and then if you're interested, you can cycle back to the, the idea is that simple, and we apply that everywhere throughout the network. If you want more details, please jump to the archive paper. Here we see performance on a very simple task, CFAR 10, with just adding Gaussian noise to the model. Maybe we'll call this an investigation in robust deep learning. We're going to now look at very small domain shifts, which are just added noise. I think people, when we use small domain shifts, people usually call it robust deep learning. When we use large domain shifts, you call it domain adaptation. I don't care what we call it as long as it works. Here we see performance of a CFAR 10 network before adaptation in orange, and the true class is highlighted in red. So on the left, presenting a 3 to the network, it actually tended to think it was a 6, just because of Gaussian noise corruption. And after this fully test time adaptation method that I've just introduced, the model actually shows the performance in, shows the outputs in blue, which are at least getting it right. Have the strongest response is on the correct class. And we can see similar performance for the other 2 examples here. The initial performance has the mode of the output on the wrong class and then gets the right class after adaptation. And so this method is performs very well across these sort of very small domain shifts corresponding to robust deep learning experimental protocols. I think these were introduced in the paper from Dan Hendricks and colleagues. He's now a student at Berkeley. From motion blur through the other forms of noise here, accuracy improves dramatically with this adaptation scheme. Here's another illustration of that data. The cool thing is this model is so simple. Not only does it not require, it certainly doesn't require any labels on the target data. It doesn't require any source data or statistics of the source data, but it's a very general model. It can be instantiated, a very general trick. It can be instantiated in any number of kinds of models, and we've done that and show that there's improvement in various settings. We have some results in the paper on digit recognition. I'm going to go through these somewhat quickly so I have time for the XAI slides. Visualization of how the representation seems to be more separable after adaptation. These are the digit examples I mentioned. I'm going to now, and then of course, you know, as I teased at the beginning of the talk with the orange world slides, we have quantitative results as well on semantic segmentation from synthetic to real, Grand Theft Auto to cityscapes. And I'm sure everyone's familiar with this paradigm where we're trying to label the semantic class with a color corresponding to each pixel in an input image. The performance on the lower left shows how it can go bad. And after our entropy minimization domain adaptation procedure, it's pretty good. You can actually see it get better through the optimization steps. This is stepping forward through the optimization from the initial results to a final result after adaptation. And so that's the main story here. Our fully test time adaptation method is label-free, source-free, proxy-free, and agnostic to task and architecture. And so we're pretty excited about it. I think this is going to have a lot of impact, and we can extend it in several ways, including moving towards adaptive computation, kind of early stopping, earlier feedback, and richer tasks, as you can imagine. So if you're interested in that, there's an archive out there. I think the previous name for this project was Fully Test Time Adaptation by Entropy Minimization. I think that's the archive title, but the more recent title is Certainty as Supervision for Fully Test Time Adaptation. The other two archives are linked here. The second one is, I think, just come up. And I may have 3 minutes left, and especially because I think I put it in my abstract that I would tell you a little bit about advisable and explainable AI. I'm going to do a 4-minute tour de force on that, and as time, as Q&A time is used, I can dive into some more details. I think it's sort of a complement. I'm very excited about all of the work on unsupervised and self-supervised. It's sort of the low-level side of vision work that we do, and the XAI is very complementary to me and my group. More high-level, more pushing on vision and language in many ways, and also sometimes a trigger for certain people who don't like explanations, and I like to engage them in arguments if they're interested. This is a theme that many people are excited. How can we make deep learning more explainable and trustworthy, more than just black boxes? There's this cartoon that people have put out there for a long time, which I think is wrong, that there's a trade-off between accuracy and explainability between deep learning and pre-deep learning, and that's wrong. And I think that if you can look at the totality of results from our lab and others, and we can see that we can add explainability of various forms to deep learning, and it certainly will do no harm to those methods. And actually what we really are excited about, I'm not really excited about explanations for explanation's sake. I'm excited about explanations that improve performance of a deep learning model. And that's what we've been showing and targeting. And there's two big themes that we've looked at in our group. One is on modularity, and that's building models that can visualize what's being used to make a decision. For example, the RISE model or GradCam model. The RISE model is a more causally assertive method from our colleagues at BU. And you can inspect a model to see why did it make a decision, what was it relying on, is it making the wrong decision, or is it right for the right reasons? I don't have time to talk about this at all, but we've looked at multi-step saliency, where you have a complicated reasoning process that needs to answer a question in a vision and language task, and you unpack the different steps of that process and visualize what's being relied on at each step. This is still work in progress, but we had an ECCV paper on this 2 years ago as well. And the other half of the project, that line of work that, and this is representing several different faculty at Berkeley, I should say, and in a broader team that works across the country, is a language-based approach, going from image captioning to question answering to grounding the decision of an agent with explanatory text, justification text. And we've worked on this for many years. You can classify an image, and then you can use the internal representation that led to that classification to also generate a caption or a story for why that's true. The difference between a caption and a visual explanation is that the text is relevant not just to the image, but to a decision that was taken. We've extended this work to counterfactuals. We've also extended this work to autonomous driving, where we have, this is work in collaboration with John Canny's group, where we have a controller that's making decisions about how to steer the car, and also telling stories that correspond to what a human expert would have said when they provided training data to the model, and also assessing which parts of the image are being causally used to assess it. There's some, this is using some of the Nexar data sets as the underlying data that were then augmented with explanations, and the model can predict explanations. This is already work that's several years old. You can see the ECCV 18 paper. The most recent work that was reported in past CVPR is going from explanation to advice. And this is that transition where we stop trying to worry about just like making the user feel good about the model or trust the model, but actually making the model perform better. And by this mechanism of explanations, the system can now communicate in natural language to us. We can now communicate in natural language to the system and actually give it advice, maybe a kind of backseat driver type of thing, which is irritating to a human driver, although I guess maybe sometimes helps a human driver. But to an agent which has not been fully trained, or has been trained, for example, on data that don't fully represent the real world. In this case, the scenario is, in the training set, all the people happen to appear on crosswalks. But in the test set, there were people who were jaywalking. And the model didn't necessarily pay attention to the people as much as it should have, because it always had this very reliable cue of a crosswalk to stop in. And so by adding an advisable cue, it's not quite what's illustrated on this slide, but so bear with me on that. You could, when a person was about to jaywalk, the model would hit the person if it weren't given advice, but we could give textual advice to the person, to the model, to pay more attention to the person, or that, you know, there's a person about to enter the road, and indeed the model would then attend to that person and improve its performance. So that was a whirlwind tour of XAI. Sorry for the kind of Franken talk, but I think these are big themes, and there's lots of papers if you're interested in more details. And I think we have some time for Q&A as well. So I will stop sharing. I can bring back my slides as needed, and now I can actually look at people's images, if not their faces.
Yeah. So first of all, thank you very much. It was a great lecture, a lot of great topics. We have here some questions that people would like to ask you, and we'll just go over it. The first one that got most upvoted. In the meantime,
Sure.
I will say that you can join or ask questions or upvote in the link that we sent in the chat. So just enter it, upvote, ask your question. We'll just ask it live. And the first one that is actually very interesting. So can you share your thought on self-supervised models that imitate learning similar to
Sure.
animals, etc.?
Yeah. These are three great questions.
Yes.
I'll do all three of them.
Right.
So the first one is a great question. And when we talk about contemporary deep learning methods, even the stuff that I presented today, it's still far from human cognition in so many ways.
Yeah.
We're making them more robust, but I think we're maybe halfway there if we're being very optimistic to fully robust and human level invariant performance. And the communicate and survive part is really key. I think we've made a lot of progress on the paradigms that we have in computer vision, but they're all based on these sort of static data sets. And the question is sort of foreshadowing what many of us also believe, which is to really make the next jump forward in visual representation learning, we need to be driven by tasks that involve action and probably communication in a multi-agent setting. So I've been interested in vision and language for quite a while, how we bridge the gap from pixels to words that are in a channel to another agent or a human partner. And I think we're still in the early days of that endeavor. Even though we have cool things, and I showed you all that explanation text stuff, but how we can learn and go beyond sort of artificial sets of categories that have been defined really for I shouldn't say for no good reason, but for a limited reason that may no longer be applicable to a broad set of tasks. Like the WordNet category hierarchy is interesting, but I don't think it reflects all of human visual cognition. And how do I learn what to perceive in order to communicate to another agent? So going forward and setting up the equivalent of a self-supervised learning game in a real world, maybe even just a strong simulation between agents who have to communicate is a very cutting edge theme that probably there are papers in review right now on it, that's something we will see in the future years. Second question, how do we survive when training a state-of-the-art model costs millions of dollars?
Well, the $1 million question.
Or it's the $1 million question. Well, I think, if, the other question.
Yeah, the question
what was the third one? The third one was, what's the, now I've forgotten the third one. Anyway, how do you do it when it costs $1 million? I mean, I think you have to find the next disruptive thing. And often the frontal assault isn't, AlexNet disrupted, if those very few people probably in the field right now were in the field, as AlexNet was first being reported. If you were one of those people, you'll remember that there were New York Times articles about deep learning and how it's going to change the world. And there was consensus amongst all the big industrial players that the way to learn a deep model was to run an enormous cloud of CPUs that would optimize your representation. And I think it took more than millions of dollars. I mean, they burned down the equivalent of a small city's power grid, learning one small network for one cat. And then Krzyzewski's model came along and showed actually you can get orders of magnitude more efficiency just doing it on a single desktop supercomputer with consumer grade hardware. And now we've kind of moved back to that mode where, well, it's a huge experimental apparatus. And I think some small group or some small company, or maybe some very transformative thing will move to analog computation or, I can't predict what the new paradigm will be, but I think there will be something in the next decade that surprises us. And we're not just training models using the brute force way that we've been in the last decade. But I agree with you for this year. If you're doing unsupervised learning research, it's hard to compete without a big electricity budget and a hardware budget. And then as an academic group and being chief scientist at a startup, that is a concern. So hopefully everyone will be, the the happy answer there is that it's a pretty collaborative field, and the big companies are sharing their ideas and collaborating with us at Berkeley, at least as academic partners. And so, hopefully the research will proceed and we'll see the answers. How far are we from level 5 autonomous vehicles? At least 2 years, and maybe
really
20.
This is your, because every time you say the 2020 was supposed to be the year of autonomous. So okay.
Hey, COVID, I'll blame COVID.
Yes. Okay. 2 years. Do you have any rational explanation? This is
no. I think I'm not a great expert on that one right now. It depends on what you mean by autonomous and the regulatory. I think we already have vehicles that are fairly pretty autonomous. So like my Volvo can drive 2 or 3 hours from San Francisco to Lake Tahoe without me doing anything, but it's still far from complete autonomy.
Okay. The next question: what do you see as the next step in evaluation of CNNs?
Well, depends on what you mean by a CNN, but I guess we're talking about vision systems, moving towards the answer to the first question. How do we make going right now? CNNs are these literally discriminatively trained convolutional multi-layer models. They don't perform anything like human vision. They can't explain themselves. They're not robust to adversarial transformations. They don't exhibit common sense or capture common sense. They're trained with lots of positive and lots of negative examples, in contrast to people who generally are trained with unlabeled data and a few positive examples from human teachers. So I think the next step is moving vision models ultimately towards machines that have this sort of human level common sense, human level robustness, and human level few-shot performance.
Interesting. I hope it will happen soon. Next one.
Me too.
What, in your opinion, will be computer vision next big improvement? This is maybe similar to the last one.
Yeah, same answer.
Okay, and great. This is question. Yeah, when you approach a task which was solved well by supervised methods, how one can guess if it can be solved well by unsupervised methods? Interesting one.
I think you can guess based on, is the supervision kind of something that's very apparent in the image, or is it something that requires external knowledge? Like if I have to predict the horsepower of a car, the signal there is not in the image. Although I could train a classifier to predict the horsepower of a vehicle, it would learn what a muscle car looked like and what a budget sedan looked like. And I think that is something that's like, you need external knowledge to get that. And so an unsupervised method will have no chance. That's the only guess that I know how to make.
Okay, interesting example also. We have a lot of questions about the future. So what do you expect new tools other than deep learning evolve in the next 10 years?
So someone has to define deep learning for me. I think if deep learning means discriminatively trained convnets, then I'll refer back to 2 answers ago, which are models that are going to be more generative, models that are going to be more human inspired and have some sort of common sense, explainability. Now, if we're saying deep learning are nonlinear, jointly trained models, then that subsumes both categories. So I don't really see deep learning as being a very limiting concept. So I think basically the deep learning, period.
Okay. So the next one, do you think that the way unsupervised learning works limits its applicability?
Well, I mean, though I think that's a bit of a tautology there. The way current unsupervised learning works does limit its applicability. But that's not a property of the field.
Okay. And so we will move to the next one. This is interesting. And how could one get started in the field of autonomous vehicles while still a student? What are the recommended steps? And maybe a more broader approach, we get a lot of questions in our community, how to make your first steps in the field of machine learning.
I have an easy answer for that first one. It's apply for an internship at Nexar.
Wow, nice one. Boom, yeah, right.
But more seriously, I think that is finding an apprenticeship in an academic lab, or I mean, there are plenty of courses there's like probably a Udacity course, or there's little demos. You can dabble with little problem sets on predicting properties of images. But autonomous vehicles, if you're saying specifically the field of autonomous vehicles in contrast to like computer vision, or it's hard to do it just from your desktop. You do need to get dirty with actual actuators and vehicles, or data sets at the scale that Nexar has. And so I think while one should take all the online courses you can find, it is great if you can find a local university or a local company and sort of drop into their meetups, or if they have apprentice programs or internships. Okay,
and maybe in more general perspective, a lot of people want to enter this field in general. Do you have any more tips, advice for students?
No, I think anyone can make great contributions in this field. I think even with only a little bit of preparation. So I guess be excited and be modest, and try and find smart people to hang out with.
Sounds like a great tip. Let's go for the next one. How do you decide which metric and techniques to explore the performance of an unsupervised model?
Well, I mean, that is a philosophical question of the first order that may only be exceeded in complexity by the following question. Yeah, I mean, that's the problem with the term unsupervised learning that I think we've known, like, at least since I've been in AI, you can't define unsupervised learning and you can't evaluate it. So I think, I don't know, that's a very complicated question. And in many ways, so self-supervised feels a little bit, so, the reality is you're always assuming that you have some generic organism or agent that has to go perform in some world, like a car that's going to drive around the whole world. So we would like to be able to deal with any natural scene that this vehicle is going to encounter. But, and so in reality, we're trying to average over an infinite number of future words, right? Yeah, a fun one.
Sorry for that.
We're going to average over a whole number of future worlds.
Okay.
Oh, we've been Zoom bombed. That's cool.
Yeah. We'll just kick him out. Sorry for that, and won't approve.
That's fine. And will deep learning get us alone to AGI? I mean, again, it depends on what we mean by deep learning. If we take a narrow definition of deep learning, which is like current convnets, absolutely not. But I think deep learning will be a big part of the solution. That's a pretty good strategy.
Yeah, sorry for that. Nice. I guess we are being attacked.
And how will we override the impending AI winter? Well, I don't know. Maybe it's just a moment of summer before summer comes back. I don't know if we're in a winter yet. You have to get rid of Trevor again.
Yeah.
Kick him out. There you go.
Kick him. Yeah. Sorry for that. This is the internet.
We haven't found a solution to that yet. You think that's something that people
maybe we should invest in that rather than AGI. So I think we will just have one more question, and then we round up. Can you give more intuitive intuition about why minimizing entropy is good for domain adaptation.
Yeah, I mean, I'll kind of try and repeat the one I gave during the talk, which is hearkening back to the pre-deep learning era in computer vision, where scale space models were popular, and the SIFT descriptor, SIFT detector actually found landmarks that were good for alignment. That there's extrema, you know, that you want to sharpen your representation to find kind of the maximal points in it, and that you can do that in an unsupervised fashion, and that on top of that, supervised learning is very powerful.
Great. So I think we will just round out here. Do you have anything that you wish to say, to share to the Israeli community, or in general, thing that you would like to just add and share?
No, just I'm certainly looking forward to visiting Nexar in Israel again, and looking forward to when that becomes possible.
We hope all to do that also. And thanks you very much for your time and for the great lecture. And that's it. Bruno or Ilan, do you wish to add something else?
No, thank you, Uri, and thank you everybody for joining the talk. Thank you, Trevor, for walking us through the latest research and doing the sneak peek on explainability. I think that was very, very interesting. And hopefully, as Trevor says, soon we'll all be able to do this in person.
Yes, we hope so. So thanks everyone. Bye-bye, and speak with you soon. Bye-bye.